Today we are talking about an engineer's responsibility, and we have Don McNutt as our presenter today. Don is with the American Concrete Pipe Association. He is our Great Lakes region engineer, and Don has tons of experience. Don graduated with a civil engineering degree from the University of Cincinnati in Ohio, and he got his PE registration in 1985 and has been in the precast industry for 35 years. So Don is a wealth of knowledge, and I did just want to let everybody know we are going to be talking about plastic versus concrete pipe today. So you will hear us talk about both our product and a competitor's product of plastic, but we are going to stick strictly to the standards and what the national standards say about each of the products. So with that, I will go ahead and turn it over to Don.
Hey, Kim, thank you for that nice introduction. I'm excited to be here today to share some very important information. But before we get started, what I like to do is a little demonstration that I do when I'm in person giving this presentation. So what I'm going to do is I'm going to start with showing you what I consider to be very good soil. Actually, it's a wood block, but for our purposes today, this is very good soil. And we're going to install a flexible pipe, thermoplastic pipe, quite frankly. Well, it happens to be a peanut butter jar, but it works great for our purposes today. So what we want to do is we want to install that pipe, make sure that we get good material compacted into the haunch area for support, and then up to the spring line. At that point, you'll see that if we put load on that pipe, we're still going to get some deflection. So we don't have a structure yet. So what we need to do is complete the structure with soil all the way around and up over top of the structure, up over top of the pipe. So when we put load on this, and actually I could stand on this, but when we put load on this, the load is going to go down through the soil, through the pipe, and into the soil below. At this point, we have a complete structure with thermoplastic pipe. Now, concrete pipe is similar, but actually very different. So we have our good soil here. We're going to install our pipe. Again, we want to get that material into the haunch area for proper support, up to the spring line, and at this point, our structure is complete. We can put a load on that, and that pipe is going to carry all of the design loads based on its structural capacity. Because remember, concrete pipe is a composite member of concrete and reinforcing steel working together as a structure. We test these products before they leave our plants for strength. So at this point, our structure is complete, completely different than the thermoplastic pipe installation. So with that, what I'm going to do is I'm going to turn off my camera. We're going to get rolling on this presentation, and we're going to delve deep into the differences between plastic and concrete pipe installations. When we're going through any type of project, we're going to go through three assessments. First of all, there's going to be a technical assessment, doing the design work. Then we're going to do a financial assessment to see what is this project going to cost and maybe compare a couple different products. And then finally, what is a risk assessment? There's going to be different risks with each type of material that could possibly be used. When we go through the design procedure for any type of pipe product, we have to make sure that we design for all of these loads. They're going to be earth loads, live loads, construction loads, and then possibly surcharge loads on the pipe. Just as a quick review, we want to remember that concrete pipe is an engineered product and it is plant tested for strength. Flexible pipe, on the other hand, is an engineered installation, and you do not know what you have until you've structurally checked it in the field for deflection 30 days after installation. When an engineer is going to structurally design a pipeline, he or she has to go through the proper design procedures. Well, let's see what the FHWA requires for properly designing pipe. In a memo that was sent out to all DOT districts throughout the country, Thomas Everett said this in part: "While these requirements are routinely and rigorously applied to bridges and bridge-sized culverts, I wanted to remind you that they are also extended to other applications such as smaller culverts, structural supports for signs, luminaries, traffic signals, and buried pipes." So what are these design requirements? Well, he was referring to Federal Regulation 23 CFR 625. which that in turn refers to ASTO LRFD Bridge Design Specifications, 7th edition, ASTO 2014 and 15, the interim revisions. So what that memo says is, LRFD Bridge Design Manual must be used for bridge-sized culverts, smaller culverts, and buried pipes when doing structural designs. ASTO Section 12.10 of the LRFD Bridge Design Specification gives two acceptable methods of designing reinforced concrete pipe. Per Section 12.10, it allows both the direct design and indirect design methods. ASTO Section 12.12 describes the methods of design for thermoplastic pipes. For concrete pipe, the direct design method can be performed with longhand calculations or more simply using a program called PipeCar, which is still being used but no longer supported by the ACPA. The Ericsson Pipe program is the current software being promoted by the ACPA. Typically, the direct design method is used for installations with design parameters beyond what can be performed using the indirect design. The indirect design method correlates the field load conditions indirectly to a concentrated load, or the D load, that will produce a similar bending moment. This method can be done with the 7-step process described in the Concrete Pipe Design Manual, published LRFD fill height tables, or the PipePack software package, which is available to use for free at the ACPA website. Let's take a look at an example using the fill height table. This is the first page of the fill height tables where the design method used to prepare the table is documented. The results in these tables were obtained following Section 12.10.4.3 of the ASTO LRFD Bridge Design Specifications, 7th edition, 2014. If we look at an example of a 48-inch diameter pipe that will be installed using a Type 3 installation under 12 feet of fill, we will see that a D load of 1,300 is required. That means a Class 3 pipe will carry the design loads. At this point, our design is complete. Now let's look at designing HDPE pipe. If we look at a fill height table published by the manufacturer, we see that it looks similar to the concrete fill height table, but the information is formatted differently. They tell us that the results are based on the structure section of the manufacturer design handbook. According to their table, a 48-inch diameter pipe can be used at different depths depending on the soil embedment material that is used and how it is compacted. Note 2 below the table states that the installation is assumed to be in accordance with ASTM D2321. Note 5 tells the user that the material must be knifed into the haunch and in between the corrugations. All this information seems to be reasonable to use this table. If we take a look at the cover page for this document, the opening statement is clear that the document is only provide answers to cover height questions and that the data is not intended to be used for project design. It goes on to say that the design procedure described in the structure section, or section 2, of the drainage handbook provides detailed information for analyzing most common installation conditions. This procedure should be utilized for project-specific designs. Section 2 of the drainage handbook tells us that this section provides a step-by-step guide for the structural design of non-pressure corrugated polyethylene and polypropylene pipe. The design methodology is based on the ASTO design procedure. 3 load cases must be investigated. First of all, the soil prism pressure must be calculated for the water table above the top of the pipe and at or above the ground surface. The next calculation where the water table is above the top of the pipe and below the ground surface, and lastly the case where the water table is below the top of the pipe. Thrust must be calculated both at the spring line and the crown of the pipe. The total load, including soil load, live load, and hydrostatic load, must be considered. Both short and long-term material properties need to be evaluated due to the time-dependent nature of plastic materials. Next, buckling must be evaluated. The pipe wall must have sufficient stiffness to remain stable under compression loads. Combined strains must be also checked at extreme fibers, since bending strain from deflection creates tension in compression zones. Finally, a deflection calculation must be performed to predict the pipe deflection based on all the installation materials and procedures. The anticipated deflection must be verified with a field deflection test to verify the installation was performed properly. The maximum allowed deflection is 5%. A look at a simplified version of the modified Iowa formula for calculating deflection shows that the load is carried partially by the pipe and partially by the soil envelope. If we take an example of a 48-inch diameter HDPE pipe with a pipe stiffness of 18 psi and a soil modulus of 1000 psi, we can plug them into the denominator. When we do that, we can get a feel for how the deflection calculation works. Simple math shows us that the pipe stiffness will contribute 4% of the system strength with regards to deflection, and the soil envelope contributes 96% of the system strength. If we lay this out in table form, you will see that 48-inch diameter pipe, again, the pipe contributes 4% and the soil 96% of the strength. But if we go to a 12-inch diameter with a 50 psi pipe stiffness, which is the stiffest pipe HDPE manufactures, you'll see that the pipe still only contributes 11% and the soil 89%. And now let's take a look at the largest diameter, 60-inch diameter. The pipe's only going to contribute 3% of the strength relative to deflection, and the soil 97%. All right, now it's time for our first poll. Which calculation for thermoplastic pipe design can be verified in the field? Is it thrust, loading, deflection, or combined strains? Okay, Kim, go ahead and launch that poll. I know Kim was having issues with her computer a moment ago. I'm not sure if she's able to launch that poll or not. Ground control to Kim.
Let me get this poll pulled up here so that you guys can actually answer it. Okay, the poll is launched. I have heard in the past some people can't answer. If you'll resize your screen, that should help if you're having trouble answering it. And I know I'm still getting a few questions of sound. Sounds like if you don't have enough bandwidth to get video and audio at the same time, it might be choppy. But rest assured, we are recording this. So if you are having trouble hearing it, we'll definitely get that out to you guys in the next couple of days so you can watch with us. Give everybody a couple more minutes to keep voting. All right, I'm going to close that, share it with the audience, and let Don respond to that.
Okay. Yeah, I can see those results. 85% of you say deflection, and in my opinion, that's the correct answer. You know, issues with thrust or loading or the combined strains, those will show up in a deflection test. But really, the only thing that you can test or check in the field is going to be deflection. So I think everybody did a great job on that. Thanks, Kim. Let's move on now and talk about the key differences in pipe installations, whether concrete or thermoplastic. These two basic trench details show the similarities between concrete pipe and flexible pipe installations. With both materials, the pipe is acting as a conduit to convey liquid. With concrete pipe, the pipe provides both the conduit and the structure. The soil in the haunch area and the embedment material up to the spring line provide the support for the pipe structure. So my question is installation important? Yes, it is important. On the other hand, the flexible pipe relies on the surrounding soil envelope to provide the vast majority of the structural strength of the system. So my question here is installation important? I say no, it's critical. What do you think? There are those that will ask, what difference does it make? Well, I think it makes a big difference, and it's a really big deal. All right, let me see if I can explain this. I'm going to use a little graphic to hopefully simplify this whole conversation. When specifying the use of concrete pipe, the engineer needs to put on their plans and in their specifications to manufacture the pipe per ASTM C76 and to install it per ASTM C1479. The manufacturers manufacture pipe to C76 all day long and have no problem and say, well, that's okay. The installers will install the pipe per ASTM 1479 because it's a prescriptive specification and all of the attributes of that trench detail are described as what needs to be done. On the other hand, when specifying thermoplastic pipe, many times the engineer will put into their plans a basic trench detail with a note that says, install per manufacturer's recommendations. The manufacturer's literature plainly states that the design must be done per their design handbook and installation per ASTM D2321. ASTM D2321 includes 24 different aspects on the installation that the engineer is responsible for. So what happens is, and many engineers don't know this, but the responsibility will come directly back to them. Many times when I share this information with engineers, I kind of get that blank stare like, Don, what are you talking about? So let's go ahead and look at those two specifications and dig deep. Here we have the two specifications or standards side by side. ASTM C1479, the standard practice for installation of precast concrete sewer, storm drain, and culvert pipe using standard installations. And then ASTM D2321, the standard practice for underground installation of thermoplastic pipe for sewers and other gravity flow applications. The one thing I want you to note is on 1479, that final statement is using standard installations. This is a prescriptive standard. We're going to start out and talk a little bit about the soils that are used in pipe installations. Both specifications have tables describing the allowable soils for their respective products. They include basically the same materials but are given different names. The concrete specification, ASTM C1479, uses the term category, whereas the plastic specification uses the term class. A Category 1 soil for concrete pipe is the same as a Class 2 soil for plastic pipe. You also see that a Category 2 soil for concrete pipe is the same as a Class 3 soil for plastic pipe. Moving down the chart, you'll see that a Category 3 soil for concrete pipe is the same as Class 4 soil for plastic pipe. And then finally, the Category 4 soils for concrete pipe are the same as Class 5 soils for plastic pipe. And both of those specifications prohibit the use of those materials for pipe, embedment, and haunch materials. The significant difference between the two specifications is that the thermoplastic pipe specification includes what they call Class 1 material. You will notice that this material does not fit any of the ASTO soil groups. The plastic manufacturers promote using this Class 1 soil and just dumping it over the pipe. The material is generally used as a Class 1 material is a number 57 stone, which is open graded that is not self-compacting as many people claim. Compaction equipment must be used to properly orient the angular crushed stones. Since it is a cohesionless soil, the use of a nuclear gauge or other device is not appropriate. Studies have shown that dumping stone will only achieve 80 to 85% compaction. Compaction equipment can reduce the vertical height of a layer of stone by only about 8%. Let's watch a video put out by ADS Hancor with regards to dumping material with their products.
Other materials, including native soils not identified as Class 1, 2, or 3 materials, are generally not suitable as initial backfill materials. Regardless of the backfill used, it is always important to knife the backfill material under the haunch of the pipe to prevent voids. To help ensure even placement of backfill material around the pipe, dump the material directly on top of the pipe so it falls equally on each side of the pipe. This method will also keep the pipe from shifting during the backfill process.
It's interesting they promote dumping the stone. However, the recommended knifing process disturbs the stone and any compaction achieved by dumping is lost. In addition, dumping the stone over the center of the pipe reduces the compactive energy supposedly provided by dumping. The scope of the concrete pipe installation standard covers the installation of precast concrete pipe. This is a very straightforward prescriptive standard. ASTM D2321 provides recommendations for the installation of buried thermoplastic pipe. The standard goes on to explain that the scope excludes product performance criteria such as minimum pipe stiffness, maximum service deflection, or long-term strength. It then goes on to describe the role of the engineer to verify and assure that the pipe specified for an intended application, when installed according to the procedures outlined in this practice, will provide a long-term satisfactory performance according to criteria established for that application. All right, time for our second poll. At what point is the structural backfill complete for reinforced concrete pipe installations? Is it the middle third of the bedding, at the spring line, 6 inches over top of the pipe, or at the top of the trench? Kim, you want to go ahead and launch that poll? All right, Kim. I know we're having some lag between Columbus, Ohio and somewhere out in Colorado, but you can go ahead and launch that poll.
Some people may have different timing on their screen, but I am going to launch this next poll.
Yeah, don't you love technology?
Yeah, and somebody also gave a tip that if your audio isn't working and you're still hanging in there with us, that it worked better for them to use the call-in feature. So under your audio, you can hit phone call. It'll give you a number to call in. That might help some of you that are still having problems. But the poll's been launched. We have about 60% of folks who have voted. I also got some feedback on the last poll. People were still challenged by answering. You can always put that in your chat log or the questions. That does capture within our system, so we know that you're on and participating, because we do provide PDHs for this class, and those will go out following the webinar. But again, if you resize your screen, we've heard that helps, either up or down. All right, I'm going to close that one, Don, and let you see the results.
All right. Again, we've got some great answers here. The correct answer as far as structural backfill is concerned is the spring line for reinforced concrete pipe. Middle third, that's important to have that material fluffed up under the pipe on all pipe materials. Lets that pipe kind of nestle in, but that doesn't really create the structure or finish the structure. 6 inches over top of the pipe, that's all well and good, but that does not aid or enhance the structural strength of reinforced concrete pipe. That 6 inches is important with thermoplastic pipe. And then the top of the trench, yeah, you're certainly going to, backfill up to the top of the trench. You want to have proper compaction and such, but again, that really doesn't complete the structure as far as the structural strength of reinforced concrete pipe. So again, thanks for getting that thing loaded up and going for us, Kim.
Yeah, you bet.
Let's continue comparing these two standards. ASTM 1479 references other documents 12 times, while D2321 references other documents 24 times. It is clear there are more items to consider when working with thermoplastic pipe products. ASTM C1479 provides definitions, terminology, and illustrates all the components of a trench detail. ASTM D2321 provides much of the same information. A significant difference with the plastic standard is the inclusion of the definition of the engineer and the modulus of soil reaction E'. This standard makes clear that the engineer is responsible for the 24 items referenced. I find many specifiers of thermoplastic pipe do not realize this is even included in D2321. E' is the empirical value used when calculating deflection that we discussed in earlier slides. Both standards provide trench details and associated requirements. Let's take a look at them in greater detail. Foundation requirements are described in the text and are similar for both products. The bedding requirements for concrete pipe is a minimum of 3 inches and up to 6 inches over a rock foundation. Bedding for thermoplastic pipe shall be a minimum of 4 inches and 6 inches over a rock foundation. So not a great difference between the two specifications. Based on the standard installation used, once the appropriate material is knifed into the haunch area and properly placed and compacted up to the spring line, the installation is structurally complete for concrete pipe. As we saw in the video, it is critical to get the material knifed into the haunch area of thermoplastic pipe. According to section 7.5 of ASTM D2321, the pipe zone must be backfilled such that it does not disturb or damage the pipe, and do not let the compaction equipment contact the pipe. Section 7.5.1 says that the required percent compaction of the embedment should be established by the engineer based on evaluation of specific job conditions. The initial backfill must extend to a minimum of 6 inches over top of the pipe. The asterisk directs the engineer to section 7.6, which provides additional requirements. Section 7.6 states that it is the engineer's responsibility to determine the minimum depth of cover. If there is no engineering evaluation, the minimum cover should follow the table shown. Per the table, the minimum structural embedment allowed is 2 feet when Class 1 material is used. If any of the other approved materials are used, 3 feet of cover is the minimum allowed. Note also that the use of a hydro hammer must be approved by the engineer, and a minimum of cover of 4 foot is required for all pipe sizes. At this point, my question is, are we structurally complete? Well, how would you know? The significance and use of ASTM 1479 is straightforward. It is used as a reference by an owner or the owner's engineer in preparing project specifications. ASTM D2321 is similar in that it is used by designers, specifiers, installation contractors, regulatory agencies, owners, and inspection organizations. It goes on to say that modifications may be required for specific job conditions or for local or regional conditions. What it does not say is who has the authority to make those modifications. Okay, now it's time to get back to the soils. ASTM 1479 includes 4 standard installations, and it provides specific requirements for each installation. As an example, a Type 3 installation requires a specific bedding thickness. The material for the haunch and outer bedding area can be one of 3 different materials, each requiring a minimum percent compaction. The lower side has the same requirements as the haunch and outer bedding material. This is prescriptive and leaves nothing to question. Table 3 in D2321 provides recommendations on installation and use of the different soil classifications that I discussed earlier. A closer look at Table 3 shows the 4 allowed classes of soils. All 4 materials are suitable for the foundation of the trench. Requirements are spelled out for the layer thickness of each of the materials. All 4 classes of soil are listed as suitable for the pipe embedment zone, with certain restrictions spelled out. A closer look at Class 3 and 4 materials shows that they are described as materials that are difficult to place and compact in the haunch zone. With the requirement to reach 90 to 95% compaction with impact equipment, it is difficult to achieve that level of compaction in the haunch zone without moving or damaging the pipe. Note that the compaction requirements for the Class 1 aggregates send you to footnote C. Let's zoom in on that and see what it has to say. Footnote C says that the stone can be dumped, which means uncompacted, but worked into the haunch zone. Studies have shown that by dumping stone there will be some vertical self-compaction, but no horizontal self-compaction. That is why it is necessary to knife the material into the haunch zone. If the material is not compacted with a plate compactor, jumping jack, or other vibratory compaction device, the stones will not lock together. The estimating tool that we discussed earlier shows a significant reduction in depth of cover allowed when assuming dumped material. The engineer's calculations should take this into account. Here we are with our third polling question, and this is an easy one. Which pipe is most dependent on soil support at the haunches? Is it concrete pipe or thermoplastic pipe? Kim, go ahead and launch that poll.
Don, hopefully we grab some of that lag out of there.
Yep, now we're talking.
Okay, perfect. Launching the poll.
This is another gimme, but what are you going to do?
Gotta have some easy ones mixed with the hard ones. Also noted, if you're still having audio problems or just trying to troubleshoot here for different folks, make sure you have everything closed out on your computer. That does help make the audio a little bit clearer. All right, this was a quick one, so I'm going to go ahead and close that one and share it with you, Don.
All right. 90% of the people say thermoplastic pipe, which I believe is the correct answer, and 10% say concrete. It's important, quite frankly, to get the material into the haunches on all materials. But I got a video coming up on this next slide that I think is going to tell a nice tale, and it'll reinforce my thoughts. So anyway, thanks, Kim.
All right.
This video does a great job of illustrating the importance of knifing material into the haunch area for thermoplastic pipe. Notice how crushed aggregate performs when dumped adjacent to the pipe. The material will have a natural angle of repose and leave a gap and provide no support in that area. All of the work that was done developing the standard installations for reinforced concrete pipe take this into account and are designed accordingly. On the other hand, plastic pipe products have no built-in mechanism to account for this gap. Therefore, knifing material into the haunch is critical. The bedding material size for concrete pipe is limited to 1 inch when the bedding is less than 6 inches thick, and 1.5 inches when the bedding thickness is greater than 6 inches. Flexible pipe installations allow material passing 1.5 inch sieve for their bedding materials. Since the corrugations are so close together on small diameter pipe, D2321 section 5.4 sends you to the appendix for additional information. Appendix section X1.9 limits particle size to 3/4 inch for pipe diameters 8 inches through 15. Even 3/4 inch stone is too large for 12-inch diameter HDPE pipe. The width at the bottom of the valley is 1/2 inch, and a 3/4 inch stone may block the valley before smaller particles can fill in the corrugation. When this happens, the loads will end up being concentrated loads on the ribs. Those concentrated loads will lead to long-term corrugation growth, which will increase Manning's N. Figure 3 in ASTM C1479 spells out the minimum trench width for reinforced concrete pipe. Section 6.3 of ASTM D2321 gives two equations to determine the minimum trench width for thermoplastic pipe. This table is a comparison of the minimum trench widths required. Both standards also include a note that the trench width must be great enough to properly compact the embedment materials. The appendix in ASTM D2321 states that if poor soil can sustain a vertical cut, the trench width must be increased 1/2 pipe diameter on each side. This makes the total trench width to 2 times the outside pipe diameter. Let's look at the quantity of material required to complete the structure of reinforced concrete pipe. The 48-inch diameter pipe that was shown in our earlier discussion will require 9 cubic feet of soil per running foot of the pipe installation. A Type 3 installation allows the use of any type of the 3 categories of soil listed in the standard. Quite often, in situ soils meet the requirement of a Category 3, meaning no additional embedment material will need to be purchased. The 48-inch diameter plastic pipe will require over twice the amount of purchased material than reinforced concrete pipe. If poor soils are encountered, over 3.5 times more material will be required than for the concrete pipe. In addition, plastic pipe will generally be limited to only Class 1 or 2 materials, since Class 3 and 4 are so difficult and labor-intensive to install properly. For embankment installations, both pipe materials require an embankment width of 1 pipe diameter on each side, giving a total width of embedment material of 3 pipe diameters. The significant difference between the two installations is that reinforced concrete pipe only requires the embedment material up to the spring line, whereas the plastic pipe must have a full soil envelope as shown in the appendix detail. This means almost twice as much material and effort must be provided to complete the structure. The same embedment material selection issues are the same as described in the trench installation comparison. ASTM D2321 section 6.4.2 addresses the moving trench boxes to not disturb the pipe and its embedment. It goes on to say that movable supports should not be used below the top of the pipe zone. Before moving supports, place and compact embedment to sufficient depths to ensure protection of the pipe. As supports are moved, finish placing and compacting embedment. To get from the sketch on the left to the final structure on the right is a situation where the engineer and the contractor are going to have to work together to put a plan in place so the soil and the pipe are not disturbed. The pipe manufacturer has a solution for when the box is dragged. They recommend using well-graded granular backfill material at least 2 pipe diameters on either side of the pipe and compact it to 90% standard Proctor density before moving the box. This is a visual comparison of the trench widths, whether the trench box is lifted, which allows ASTM minimum trench width. If the trench box is going to be pulled, a trench width of 5 pipe diameters is required. The standard for concrete pipe installation requires a moderately firm to hard in situ soil, stabilized soil, or compacted fill. For flexible pipe, the standard says that the engineer will determine foundation and bedding requirements according to conditions in the trench bottom. Both installation standards require unstable trench bottoms be stabilized. The plastic standard states that the engineer must determine the depth of excavation and whether the material will be replaced with Class 1 or Class 2 material. ASTM 1479 is a prescriptive standard which provides exactly what is required, including bedding, haunch and outer bedding, and the lower side requirements for the 4 standard installation types. ASTM D2321 says that the engineer should establish the embedment % compaction required for specific project conditions. Appendix section X 1.6.2 states that embedment compaction requirements should be determined by the engineer based on deflection limits established for the pipe, pipe stiffness, and installation quality control, as well as the characteristics of the in situ soil and the compactability characteristics of the embedment materials used. It goes on to say that the engineer should verify that the percent compaction specified meets performance requirements. The information in Table 3 will provide satisfactory embedment stiffness and is based on achieving an average modulus of soil reaction E' of 1000 psi. During installation and compaction, soil densities should be tested to verify that the design compactions are being achieved. The plastic pipe manufacturers provide information to alert engineers to the possibility of flotation of these lightweight pipe materials. This is an example of 36-inch diameter HDPE pipe that floated out of the ground. It would appear that flotation was not considered when the calculations were performed. If calculations are not performed, D2321 section 7.6 provides minimum cover requirements. For 36-inch diameter HDPE pipe, the minimum cover should be 36 inches regardless of embedment material used. If flotation is a possibility, the manufacturers provide details for holding the pipe in place. Here, straps are being placed to hold the pipe down. When flowable fill is used in plastic pipe installations, flotation must be accounted for. Again, straps are placed to hold the pipe in place. C1479 addresses safety and states that the ends of the pipe should be covered at the end of the day to prevent access by animals, personnel, soil, and debris. The cover should be braced or fastened but does not need to be watertight. A cautionary note is provided that if the pipe is plugged watertight, flotation should be investigated. If flotation is possible, appropriate measures should be taken. The ACPA has a document that addresses flotation and provides calculations for your use. In very rare cases, concrete pipe has floated. This photo shows RCP that floated during an earthquake event in New Zealand. Section 15 addresses manholes and fittings and their installation to minimize differential settlements between pipe and manhole and between pipe and fittings. This grouted type of connection has been used successfully for decades. The pipe, catch basin, and grout material are all cement-based products, so the grout will properly bond and like materials will expand and contract at the same rate. ASTM D2321 also addresses manhole conditions as well. This photo shows an installed manhole with a 36-inch diameter HDPE pipe grouted in. The contractor called the manhole manufacturer and said that the manhole was leaking. When they investigated, they learned that the pipe had pulled away from the grout. The coefficient of thermal expansion for HDPE is about 13 times greater than that of concrete. Let's assume the pipe sat in the sun on a nice warm summer day and reached a temperature of about 110 degrees. After installation, a soil temperature of 50 degrees would be reasonable. If we assume this 60-degree temperature differential, the 36-inch diameter pipe would reduce by about 5/16 of an inch. Section 7.10 manhole connections says use flexible water stops, resilient connectors, or other flexible systems approved by the engineer to make watertight connections to manholes and other structures. This slide shows a variety of connectors available to satisfy the flexible connection requirement. ASTM D2321 section 7.11 has an in-depth listing of items that should be monitored by the engineer to comply with contract documents. Items that should be monitored by the engineer include trench depth, grade, water conditions, and the foundation. The engineer should also be monitoring embedment and backfill materials along with the density of materials in place. The joint should also be monitored by the engineer. The same temperature differential discussion with regards to manhole connections is also relevant to pipe joints as well. For a 60-degree temperature change will cause a 20-foot length of HDPE pipe to shrink about 1 inch. Even if it's only a 30-degree temperature change, the pipe will shrink about a ½ inch in length. Keep an eye out for wide joints when reviewing post-installation videos. Finally, an item that many engineers do not realize is part of their responsibility when specifying thermoplastic pipe installations is that safety should be monitored by the engineer. Well, it appears that we have two culverts that are complete. One reinforced concrete pipe and the other HDPE thermoplastic pipe. The question is, was our installation successful? How would we know? The answer lies in post-installation inspection of all pipe materials. ASTM 1479 advises the owner to provide adequate inspection at the construction site. The appendix in ASTM D2321 states that the engineer may require deflection testing to ensure specified deflection limits are not exceeded. It goes on to say the standard recommends allowing for stabilization of the pipe soil system and then perform a deflection test at least 30 days after installation. The real question is, what is the correct method for doing post-installation inspection of all pipe materials? The appendix of D2321 describes optional devices for deflection testing, which include electronic deflectometers, calibrated television or video cameras, or a properly sized go, no-go mandrel. All pipe types should be inspected visually or with closed-circuit TV on pipe sizes that cannot be entered. Since deflection testing is irrelevant for concrete pipe, it is only required for thermoplastic pipe. Closed-circuit television cameras should be equipped with laser micrometers to be able to measure cracks in concrete pipe and joint widths in all pipe materials. Although crack widths below 5/100ths of an inch are not generally considered attainable, ASHTO does not require any action on cracks smaller than 1/10 of an inch. For thermoplastic pipe deflections, laser profile equipment will provide better information than the simple mandrel. The laser profiler will provide actual deflection values along the entire length of the pipe. Okay, last poll of the day. Who is most at risk if no post-installation inspection is required? Is it the contractor, the engineer, the owner, or the pipe manufacturer? Kim, go ahead and launch that poll.
One launched. All right, everyone should be able to see that. All right, let me share that with you, Don.
All right. Interesting. Okay, the winner is the engineer, or maybe that's the loser. The owner next, and the contractor has 5%. This one's kind of a tough one. It depends. You know, long term, the owner, I think, is at most risk if they don't require their projects to have post-installation inspection, because they're going to own it, you know, 2 years, 3 years, 5 years down the road. Immediately, a lot of times the contractor has the greatest risk, because if a problem shows up right away on the job, you know, the contractor may be at risk if there's no inspection done. And the engineer, ultimately, if it turns out that there are structural reasons in the design, then yeah, the engineer is at risk. So, and it's interesting, nobody pointed the finger at the pipe manufacturer. You know, a lot of times the pipe manufacturer, regardless of material, gets drawn into problems if there's no post-installation inspection done. So this one's kind of broad. You have to think about it. Think about what your role is in the whole process and how you want to reduce your risk. So that's kind of a tricky one, but it's interesting how those answers came out. So, you know, thanks for that one, Kim. Well, regardless of the pipe material used, it is important to inspect all pipes to know what you own. As we wrap up the comparison of these two installation standards, We know that ASTM C1479 is a prescriptive standard, and everything needed for the proper installation of reinforced concrete pipe is spelled out in detail. On the other hand, ASTM D2321 provides recommendations for the installation of buried thermoplastic pipe. In addition, it goes on to say, since there are numerous flexible plastic pipe products available and the inherent variability of natural ground conditions, achieving satisfactory performance of any one product may require modification to provisions contained herein to meet specific project requirements. Well, based on what we just learned about the installation of thermoplastic pipe, it appears that the engineer plays more of a role than just putting a note on the drawing that says, install per ASTM D2321. So I have to ask this question. What is an engineer to do to protect your license when designing underground pipe systems? Let's start with reinforced concrete pipe. It's an engineered product. First, determine the in situ soils. Then select the installation type. With that information, you can determine the strength class required. Specify the pipe class and installation type required, and then specify post-installation inspection. When designing with thermoplastic pipe and engineered installation, the engineer must do the following: determine the in situ soils, design the pipe based on in situ soils or borrowed materials, determine the compaction required for adequate structural capacity, calculate anticipated deflection. Then the engineer needs to determine the bedding requirements based on field conditions and determine trench width based on surrounding in situ soils. Next, the engineer must verify whether the depth of cover is acceptable for flotation. If there are connections to manholes, the engineer needs to specify the proper flexible connectors. Throughout the duration of the job, the engineer must be prepared to conduct field monitoring, which includes verifying proper trench depth, grade, water conditions, the correct materials are being used and compacted per the design, that joints are properly made, and that safety procedures are being followed. Last but not least, the engineer should specify deflection testing for all installed pipes to verify that the pipes are installed properly and the designs are valid. That brings us to the end of this presentation. I realize there's a lot of information there, and I appreciate you sticking with me through this whole presentation. I believe at this time, Kim, I think we're going to turn on our cameras and take any questions that the crowd at large might have. I'll tell you what, Kim, the technology is something else, isn't it?
It is. Yeah, it's unpredictable, right? Well, we do have a couple questions that we had throughout the session. Certainly, if you guys have more as you're thinking through the presentation right now, feel free to chat with them in the question pane. Before we get to questions, because we are running up against the top of the hour with some of our technical difficulties today, I did have two last polls that we wanted to get some information back from you guys. So I'm going to launch those in case somebody has to hop off before we get to questions. I'm going to go ahead and launch that first one. And the question there is, when was the last time your drainage specifications were updated? Did you update them in the past year? Has it been 1 or 2 years? 3 to 5, or maybe more than 5 years? Give everybody just another minute or two to answer that. All right, I'm going to close and share that. And so it looks like we had a good split between 1 to 2 years all the way up to 5 years longer. That's actually better than I think we see a lot of times. I don't know if COVID has helped us with that 30%, the 1 to 2 years. You guys maybe are working on them now, getting those updated. But that's good to see that 30% has been done, actually 45% in the past 2 years. So that's not too bad. Let me do one last question. So this one is that ACPA provides specification reviews to our engineering community. And if you're interested in taking advantage of those, we'd like to know about it. We'll certainly have somebody reach out to you and help take a look at your specs and how those are looking. All right, that's a pretty quick one. So we'll go ahead and close that poll. Certainly, if you answered yes to that, we will be reaching out to you to get those questions. So last few announcements before we get to questions. We will hold an ethics webinar. I know a lot of you as PEs need an ethics webinar each year. We'll hold that in December. We do these every other month. So we are in the end of October. We'll probably try and shoot for earlier December, just with Christmas coming up. And so be watching for that invitation. We also have a pipe school coming up in February, so a little bit farther out, but it will be virtual this year. So that may give you guys a lot of opportunity to come join us for a few days and learn more about concrete pipe. It will be complimentary to all engineering guests. So be looking out for that. And if you have a relationship with one of our engineers, certainly feel free to be on the lookout for that. But when it is launched, it'll be another couple weeks for registration. You can find that at at pipeschool.org. And we'll talk more about that in December. All right. Last announcement is we do provide PDHs for this webinar. We will send those out to you in the next few days. If you were able to join us for at least 50 minutes, that's typically the requirement by the licensees. So we can capture that information and send that out to you. We'll also have this recorded and posted to our website in the next few days, so you can find it there if you were having audio problems. All right, let's turn this back over to Don and a few questions we have here. Don, the first question we had is, are the earth loads calculated differently for thermoplastic pipe versus RCP?
The overall depth is the same, but as far as how the loads are calculated, I believe they are different. To be honest with you, I'm no expert on thermoplastic pipe. I did a lot of research on the specification when I got into the concrete pipe industry, so I could understand what the requirements are for thermoplastic pipe installations. But I believe the arching factor, I believe, is different for thermoplastic pipe because of the way it deflects. I think there are actually some load reductions on thermoplastic pipe. I can't guarantee you that, but that's the way I understand it. I've never been through a longhand calculation. I've seen, stacks of paper that go through longhand calculations, and I know it's pretty significant. But I believe there is a reduction with the thermoplastic pipe.
Yeah, thanks, Don. I would say, the load, obviously the soil weight over the pipe is the same for concrete versus plastic, but the pipe itself sees that load differently, and that is because of a rigid versus a flexible structure. And so there are definitely different calculations for calculating what that load would be for either product. Another good question here is, are bridge size culverts the same across the country? Bridge sized culverts.
I believe it depends on the state. If I'm not mistaken, I think 10 foot span can be a criteria for bridge. And I believe it is different in some states. That's as far as I can answer that question. You might be able to help me out. Yeah, you're not making me look good here, Kim.
I'm sorry, Donna. We're a team here, right?
Here you go.
FHWA specifies a 20-foot span, but Don is correct. Different states have different criteria for considering a culvert a bridge. Colorado is actually down to 4 feet, but we do like to follow FHWA's 20-foot span, especially if you're going to load rate pipe. All right. Let's see. Here's another great question, Don. Can you explain why the engineer does not have responsibility for the installation or design of RCP when different classes and installation types dictate the class of RCP?
Well, I think ultimately the engineer is responsible for the design of all pipe. If you have a certain fill height and you specify an installation type, yeah, you're going to specify a certain strength class. Now, it's up to the manufacturer to manufacture that pipe to that strength class. So I think the engineer does have responsibility in that regard, no question about it. But the standard installations have standard criteria that if those aren't followed in the field, then the installation is not going to be valid for a type 1, type 2, type 3, or type 4 installation. But yeah, the engineer does have responsibility, but I can tell you, you've just lowered your risk by using reinforced concrete pipe versus thermoplastic pipe, because you know what you've specified has a certain structural strength when it leaves the plant and goes out into the field. With thermoplastic pipe, you know that the vast majority of the strength of your design is going to be based on what the contractor does in the field and how they build that structure. So yeah, the engineer still has responsibility, but boy, your risk has dramatically decreased when using reinforced concrete pipe.
Yeah, that's a great point, Don. You know, I think the other thing that sometimes reduces the risk of the engineer is a lot of times as a manufacturer of reinforced concrete pipe, our manufacturers are asked to stamp those projects. And so the engineer itself for that product is responsible for the pipe to make sure it is that structure Don talked about when it leaves the facility, because flexible pipe is not that structure being delivered to the site, that it's built in the field. That responsibility maintains and is kept on the engineer of record. Great question. Let's see, another good question. Can concrete pipe be used in very steep slopes? Contractors may prefer to use PVC due to load and installation.
Yeah, it can be used in a steep slope, but you certainly want to have a method at the bottom and I don't know what, anchor rings around them, if you will, up the slope to help anchor that pipe. But yeah, concrete pipe, and I can't give you a cutoff point, but I've seen and been asked about some pretty steep slopes that our manufacturers have said, yeah, we can do that, but we have to make sure we have certain details in place to keep that pipe secure.
Yeah, great point, Don. Well, we are just about 10 minutes past the hour, and I want to be respectful of everyone's time here. Great questions. We had another handful of questions in our log. So we will make sure to reach out to you guys and get these questions answered, but feel free to reach out to anyone at ASCPA. We're always happy to help you guys. And again, be watching for our next invitation, which will come out probably sometime in November for our December webinar. Thanks so much, Don. You did a great job. Appreciate all you do for us. And we'll see you guys in December.